Thank you, Ignacio, for coming to our 8th episode of Trace Talks. We're super thrilled to have you. I know you were here for DesignCon, and I'm so happy you took out time in your busy schedule to be with us today.
Thank you very much. Thank you very much for welcoming me. Thank you very much, Lucy, for organizing this. I'm very happy to be here.
Okay, great. Can you give us a couple of sentences background of yourself, Ignacio, and why you got into EMC in the first place?
Yeah, sure. So I'm originally from Spain, but today, I live in Munich. In my past life, I have been hardware designer, electronics designer, and EMC consultant or EMC troubleshooter. So supporting customers in different industries, medical, industrial, automotive, to solve EMC problems, but always with a strong link to the design stage. So going to the lab, but also going back to the office to redesign the systems so that the production in the end is not just a set of patches, but that is sustainable and that it's optimized. And why I joined. So I started when I started to work on EMC. So I started with a project sometime. So in my first project, because I work on magnetism when I was studying on magnetism, and then somebody thought that I was going to enjoy it. So, and that's true. And then since then I became the EMC guy here and there.
That's great.
Wonderful.
Well, thank you.
Very good.
Thank you.
I'd like to know, how did you enter the field of EMC?
Okay, that's a good question. And I will say that as many other EMC people, it was a matter of accident, or it was kind of accident. So I did my master thesis on magnetics. So I developed and built a magnetic sensor. Mm-hmm. And then a few years later, I joined a company in Spain that were working on aerospace projects. And they told me, you like magnetics, so you are going to take care of the EMC campaign of this new project, which was a complex electronics control unit for a plane. And then it was kind of a big project, and it's true. I like magnetics, I like EMC, and then since I worked for a year or 2 years in that project, I became the EMC guy around. And then the life escalated, and here I am.
So you basically acquired the reputation of being an EMC expert before you truly became an EMC expert.
That's right. Yeah.
It happens.
Yeah.
Professionally, it happens.
Yeah, it happens.
People are ready to find props somewhere or the other.
Yes.
Yeah.
That's great. So, early on, what were your troubles with EMC and learning EMC? Because, the truth is we want to educate as many designers as possible.
Yes.
We want to have good designers who are aware of many pitfalls, mm-hmm. not just EMC, but other things as well.
Yeah.
Okay, but since you're the EMC expert in this case, we're going to, so answer from that perspective. Like, how can a designer, using your experience, how can they learn from that and not make those same mistakes? How is your
especially
journey?
a PCB designer?
Yeah,
PCB designer. Yeah. So, I can relate because I was originally a PCB designer. I am still designing PCBs and systems.
Okay.
And so one of the biggest challenges was to find a good source of training resources. So because there is a lot of information out there, but it's true that it's hard to cut the noise. So it's hard to know which kind of information I can use for my specific design and which kind of information I should ignore completely.
Okay.
So at some point, with the help of some mentors and people around me, so I managed to take what was worthy and forget the other information that was useful maybe 30 years ago when signals were slow.
Right.
And
fast.
And now and then use what is applicable today.
So give an example if you can. Like what's relevant today? What's the most important today?
Related to PCB design or to
PCB design and EMC.
Anything EMC.
Yeah, PCB design and EMC is what we're talking about.
Yeah. So grounding. So
Yeah.
if I need to choose just one topic, so if I need to start focusing on just one thing, I will take out grounding.
Let me understand.
Yes.
Now grounding is a very kind of a word which is least understood, in my opinion, by most people. We are talking of the grounding of the electronic circuit board or the ground layer or the ground point on the circuit itself, and also the equipment and other things, and the cables, and, etc. So please elaborate on that.
So there is already one or two terms that people confuse a lot. So as you said, so that when we talk about ground, is really the earth, so the connection of the building to the physical earth, and then back to the systems. And so there is already one point of confusion, and then the second is, so it's the reference point of the PCBs with the power
Reference voltage to which all the power rails are related to.
With the power supply.
So basically, what we normally call as the ground plane.
Can be the ground plane, but then you start mixing. So it's easy to start confusing ground plane, reference plane, ground point, the start. So there are a bunch of terms that people use
interchangeably,
and they mix. And I think that there is a lot of confusion out there. So if people need to focus on just one point, it's really to work a lot on how to define grounding topologies. So
what are the guidelines for a good grounding system?
In 2 minutes.
In 5 minutes.
Or half an hour. It's up to
or
you.
half an hour. No, that's
yesterday. I was watching the hearings, the Senate hearings of Mr.
Yeah.
Trump. So he gave only the senator 2 minutes.
Okay. So 2 minutes
to read a complete document.
That's perfect. So we have grounding in 2 minutes. So first of all, so designers need to know what kind of system they are designing. It's AC, it's DC, it's high speed, it's low speed. So to start understanding how...
Let's say it's a high speed.
Let's say that's high speed. Okay, like high speed PCBs, right? Like some of the ones...
And let us say it is analog, digital, all mixed.
Analog, digital. So as yesterday, so Daniel Vickers was saying in one of his talks, he was saying the magic, everything is on the space. So because energy, so when we increase the speed, we are not talking anymore about electricity. We need to start thinking about fields. So that means that we need to take care about ground planes, but also we need to take care about the electrics. So we need to designers need to take care a lot about how waves propagate on the PCB. So that means that can be through air or can be over the dielectric.
I believe they are guided by the transmission lines.
But then they need to design properly the transmission lines. So no gaps, no...
Uniform.
Yes. And
uniform characteristic impedance and so on and so forth.
Control impedance, yeah.
Good. Mm-hmm. Let's say all that is taken care of.
Okay.
And you have transmission line, and you have a ground plane underneath in the next layer.
Okay.
Or if it is a strip line, then you have a one plane here and one plane here, and signal is transmission line is over here.
Okay.
How these structures impact the EMC compatibility or EMC compliance?
Yep. So on EMC, what we look for is to uncontrolled energy. So that means that...
Radiated energy.
Radiated or conducted. So in the end, energy that should be in the system that is going out of the system. Okay. So a system radiates when it does not have a controlled return path. So
it does not have
it does not have a controlled return path.
Okay.
So that means that the signals wants to go outside, and then they start looking for a return path, but it's too far. So then it's when systems radiate. So if a designer takes care of that and manages to keep all the energy inside the system, then they are compliant. They pass EMC.
As a principle, that is fine. The most designers won't understand how to do that.
That's the challenge, also, because there are a lot of documents out there. There are a lot of videos. Yeah, you need to respect this, that. But the problem is that every system, every new design is different. So then designers face the challenge that okay, but my system has not this situation or has not this another situation. How can I solve that? And I think that there is a gap, that there are not good training resources to learn how to apply generic recommendations to their own designs. So that's where main designers.
So if the designs make generic rules not applicable, is that what you're kind of saying? Like based
There must
on
be some rules of thumb.
there has to be rules of thumb. That's how I live.
It's so. I don't say that they are not applicable, but sometimes it's so they enter in conflict, because there is one guideline saying, yeah, you need to keep analog and digital separated.
Give us an example.
Yeah. So
A guideline says something, and actually it should not be that.
Or a conflict of two guidelines.
yeah. So
Yeah.
there is a huge misconception. Or there is one that we have inherited since 40 years ago, which is the recommendation of splitting ground planes. Like you need to keep analog ground planes far from digital ground planes.
The digital ground. That means have them separate.
Yeah, but then the question is how? How do you separate them? Are you just not connecting them together? Then
Connect them at only one point.
or not. So, or you add galvanic isolation because you are really separating them. So there are,
But at some place in the circuit,
yes.
analog and digital are going to interface together.
Okay, so that's one streamline. Then there's another guideline coming and telling you that you need to keep a solid ground plane, but you need to be careful that analog and digital areas are far enough that the return currents are not.
That means they are
Yeah.
locational wise
Yeah.
separated from each other.
So then what do? That's where designers struggle a lot.
Maybe you can cut a little bit.
How much? How little?
Okay,
And
that is for you to tell us.
How do you do that respecting the PDN requirements? How you do that respecting the...
Assuming, let us say, PDN is not a problem.
Okay, we don't have power issues. Yes.
Let's say PDN is not
Yeah.
the issue.
Okay. So normally today what we should do is that we keep everything with the same ground plane. There is no need to keep analog digital ground planes, but zoning is very important, very, very important.
My gut feel is that the people like the advice to keep them separate comes out of the fact that analog signals may be very low amplitude signals,
They are sensitive.
sensitive, more prone to smaller noise, while digital signals, because they have a reasonably good noise margin, so they can tolerate all kinds of noise. So
Yes.
if because of digital signal switching, a lot of ground noise is created,
Yeah.
it can enter the analog stream and it can affect their functioning.
But you can keep them, so you can keep them with the same ground structure, let's say, but separated in electrical distance. So
Locational wise.
Yeah, locational
That
wise,
means keep
yeah.
the analog portion here and the digital
that
portion.
can be, yes.
elsewhere.
But no need for using AGND, DGND, and then
I see.
mixing them
I
all
see.
together.
So let me ask you this question then. If an electrical noise gets generated, a switching noise gets secreted in a digital ground plane, and let us say this is an IC and this is getting generated over here.
Okay.
How far distant does it travel on the ground plane
Okay.
to remain significant?
How far
and-
is
roughly,
far, right?
rough.
How far is far? That's the question.
How far is far?
How far is far? So with electromagnetic energy, you always need to think about wavelength.
Okay.
So depends on the frequency.
So whatever is the wavelength, how many wavelengths then?
So you were asking about rules of thumb. So normally, critical wavelength or critical distances is a 20th of the wavelength. So it's
Right.
there when you need to start comparing distances with noise frequency. So then when a distance becomes dangerous for a given frequency.
So roughly, if it is of the order of, lambda by 10 or 20,
10, 20,
then
something like that.
till that time it is significant. Beyond that, you can
you can play. Yeah,
You can play around?
Yeah, we can play. Yeah, yeah. But also that's another point of confusion, because if you open 10 application nodes, you find 10 different values.
That is where the confusion arises.
Yeah, yeah.
Because the application notes are written by not very expert engineers.
They are written by people working on a specific problem at a specific moment, which is not necessarily your problem and your moment.
Okay. I think you are being diplomatic. Okay. Now, let's talk of, now, there is another question which crops very often in the minds of people.
Mm-hmm.
Let's say you have a microstrip transmission line and you have a coplanar waveguide, having.
Yeah, like this.
Yeah.
Okay.
So from an EMC perspective, which one is better? Or both are equally good? Or it depends on the circumstances?
Depends, right? Like every EMC guy answers.
You see, when you keep on telling that it depends on the circumstances, the users are not very happy.
I know, and that's why it's hard to find rules of thumb.
No, but
in general.
would you feel that a coplanar waveguide, because you have a ground guard around the transmission line,
that's going to be my.
So therefore, it would create less crosstalk, number one.
Yes.
And it will try to confine the electromagnetic energy within that guide.
So the idea is
within that space.
Yeah, we always need to find or to use the structures that try to confine the energy as close as possible.
Okay.
The problem is designers, they always have trade-offs. So the question is when you can afford to use a coplanar waveguide and when you need to be okay with a microstrip. So that's always depends on the kind of signal that you are working with.
We got a comment from one of the users.
Okay.
Just about 2 days back.
Yeah.
He wrote a big paragraph on this topic. And he says that I've used, let us say, a microstrip transmission line, and I have not encountered many problems many times because I keep
things.
About 3 wide space on both the sides vacant.
Yeah.
So I don't face the crosstalk problem.
Then that's.
But I am also told that if you have a waveguide, you will still improve it better. So he is asking for rules of thumb.
But here is my question. If he has never had problems, why he is looking for an improvement? Because engineers also tend to over-engineer a lot of things.
Oh, no. That is you see, today's world is leading towards that. Because you have to design products for the future.
Yeah.
So he is not thinking of today, he is thinking of tomorrow.
Okay.
Yeah. That's the reason why he's asking.
Yeah.
Okay.
Looking for exclusive PCB webinars, seminars, and meetups? Sierra Circuit's got you covered. We're like the VIP corner of the PCB nightclub, minus the booze, but plus some really cool experts. Join the party at proexpress.com/events and get on the list.
So, nonetheless, the key point here is, so let us say if all the other situations are the same.
The same, yeah.
I have a coplanar waveguide.
Yes.
And I have a microstrip. And if I start measuring the electric fields at 5 meters away, for electromagnetic compliance.
Far field.
Far field, or near field, whatever. I don't know. The near field is.
I am happy with far field for EMC.
Okay.
Yeah.
Fine. So far field. So which one would likely be better?
That's a tricky question on the fly. So coplanar. Yeah.
Coplanar would be better.
Yeah. Also, are you talking about so in between planes? So
no, there is a ground plane down.
Okay, there's in both cases. Yeah,
in both cases.
But in the coplanar, you are bringing the
coplanar waveguide with a ground plane.
Yeah.
Now, of course, there are coplanar waveguides without a ground plane.
Yeah, but you are reducing. Yeah, you are confining everything.
Okay. Now, the another question which comes very often is how to stitch the coplanar grounds.
How many vias?
What is the pitch?
Okay.
of,
Yeah.
the distance between two adjacent vias.
Between
on the-
consecutive vias.
Yeah.
So also here
Is
so-
lambda related?
Yeah, it's lambda. It's always
So
lambda.
lambda by
lambda
what?
related. In all PCB design, what we need to look for is for wavelengths.
Right.
So, and also for this, there are different rules, but also lambda tenth is a good
Lambda by
sign.
10.
It's lambda by tenth. So if you have a signal, the only thing that you need to be careful is that when you are switching a signal, you don't have only the main frequency, but you will have some harmonics.
Some harmonics.
So it's good to be conservative. So to consider a few harmonics up there. So not just the.
So
the
as
frequency.
small a stitch,
Yeah.
pitch you can
Yeah.
afford
Yeah.
from both fabrication
Yeah,
and other perspectives.
That's yeah.
Okay. Now suppose you do not stitch like that. What
Okay,
happens?
yeah.
What happens?
So stitching is so it's the same as when you you add some barriers to your window.
Mm-hmm.
So if the bars are separated long enough, you can go through them, and if they are so close, there is a moment that you cannot go through them. So it's the same for signals and noise.
Oh.
So you are going to let the energy go away.
So the energy gets more confined.
Yeah, that's the idea.
If it
Yeah.
is better stitched.
Yeah.
If it is not stitched better, then it will likely not be as confined.
That's so it helps.
Could it also be that the ground plane, the coplanar ground can also become a radiator if it is not stitched properly? Antenna?
Wait.
You know.
Yeah.
I mean, you have a copper strip
Yes.
and it is not connected anywhere on the other side.
Okay. So you mean so that if you have a coplanar wave and you don't use at all any.
I mean, let us say you just have a couple of stitches here and there, without any order.
But not very careful, right?
Yeah, no.
Depends. So if you are adding them very close to the edges,
Mm-hmm.
you are going to let the fringing fields go away from the PCB. If they are somewhere in the middle, okay, it's there, as always, it will depend on the frequency, right? But at some point, the problem you will have is that, so here I'm imagining that you have absolutely nothing else in your PCB, but you will have, for sure, more traces, more components.
Right.
So the energy is going to impact all on the other components. So in the end, we need to keep the energy like only in the way they need to be.
Is it critical transmission lines, high-speed lines? Is it better that they run on the inner layers rather than on the top layer? High-frequency lines? I mean, is there any...
Depends on the stack up, for sure. The challenge would you have when you add the critical signals on the top or the bottom that they are exposed.
Yeah.
And
So they will
both-
possibly
and-
radiate more.
It's not only that, but the challenge you have is that when doing the immunity test, so in the immunity
Compliance test.
in the immunity compliance test, you are introducing directly applying high electromagnetic energy on the PCB.
Okay.
So if it's directly visible and it's not protected, then there are chances that you fail that test. So if you have the space and you have if you have a dense PCB or relatively complex stack up, so put them inside.
Okay.
If you can afford that, then that's the that's
So
the best solution.
So from what I'm hearing means that if you're really very concerned about the EMC and all, if you can somehow afford a complete ground plane on the top and bottom layers,
So
it
I
may
will
be better.
the challenge with ground layers at the top and the bottom is that they are very fragmented because you have components.
Yeah.
And so then the copper is not very well connected.
Okay.
So the best, I imagine that we're working with a 4-layer board.
Uh-huh.
So the best is to have 2 inner ground planes there.
Two
so
inner
the second and third.
Right.
And then try traces top bottom.
Okay.
But in a 6-layer, then you
Six
could
layer,
try
then.
something different.
Yeah,
You can
yeah.
still have your 2 inners,
That's a
your
thing.
signals, and then a lot of
nowadays-
ground on the outers.
Yeah,
Yeah,
but
yeah.
you see the density of today's circuits and the try to miniaturizing things and all that becomes.
That's what. So today with 6, 8, 12, so more complex stack-ups, you can afford.
Sure.
Let's say that the price you are going to pay for adding a few layers is not going to be as high as trying to fit all together in a less count layer PCB, but then failing EMC and having SI problems.
Another thing which we see commonly is, these ferrite beads or some kind of things that, wherever the cable is coming or the power cord is coming.
The cable ferrites.
Okay, so now can you please elaborate on that? Because that is very important.
Here we have some. No.
Most of the power cables nowadays come with a ferrite bead there.
Yeah, so because I have used some of them to pass EMC tests, so.
Oh, I see.
Yeah, so one of the most common problems that provokes a failure on EMC radiated test is common mode noise. Mm-hmm. And then ferrite beads, so they are magnetic components.
So common mode noise is a big culprit in compliance?
Yes.
I see.
Because a few milliamps.
That means by common mode noise, as the name says, is a noise on the signal as well as on the return path.
Yeah, as well.
And in the same direction.
Yes, that's correct. And the problem is that with a few milliamps of common mode noise, you already fail radiated emissions test. That's why it's very challenging, because you might be designing high power systems, so some 100 amps.
Correct.
And then you have a few milliamps common mode
like
noise.
Like stepper motor switching.
And then you fail test. So that's the huge challenge. So as a last resource, you can use a ferrite bead on the cable, and then you can reduce the common mode noise going over
we many times put a lot of ferrite beads on the printed circuit board also.
That's also another use. Yes.
Nowadays,
so
ferrite beads are used very often.
So on the cables, so when a product has a ferrite on the cable, is because they went to the EMC lab, they used a ferrite bead to pass the test, and then that product has been incorporated into production forever. Right. And so that's why ferrite beads come into the bill of material of a system. Oh. Normally that's.
So if let us say. There are 2-3 examples of these cables I will give you. Mm-hmm. One is, of course, let us say the 12-volt DC power is coming from some other source. Or an AC power is coming. We'll keep the AC later.
Okay.
The one is the power lines. Uh-huh. The other is some of the signal interfaces cables coming in. You have a USB cable, and you have some HDMI cable, and you have maybe an RF cable coming from the antenna or something like that. All those kind of things. Mm-hmm. Some of them require 50 ohm impedance, some of them require 75, some have 120 ohm differential, all those kind of things. Mm-hmm. And you have a lot of wires coming from sensors.
Yes.
Like, for example, you have a driver for a stepper motor, and you are having a RYB kind of syndrome. The 3 wires are running over there. Now, and the stepper motor, many times, the driver, it switches a lot of current.
A lot of energy on there.
Not very high frequency, but nonetheless, it switches that.
The energy is there.
The energy is there.
Yeah.
Now, in such kind of situations, how do you manage that?
The noise.
I give you, let us say, some signal examples, and I also gave you some power examples.
Also, so for EMC and for energy coupling, it's always a two-way road. So you want to avoid emissions, so that's why you add ferrite beads to keep the energy under control. Okay. But also you want to avoid immunity, so you can have a very sensitive sensor measuring whatever out there. Right. And you don't want that the TV is interfering with your sensor. So that's why sometimes you add a ferrite, maybe not the TV, but other power source that is interfering.
Correct.
So you can add ferrites to protect things at some connectors.
So ferrite is put into the series of the power line? In the series?
On the cables?
On the cable?
So
just in series, isn't it?
Yeah, over the cable.
Over the cables. Yeah. So is it some kind of a common joke or something, or no,
No.
or two beads you put on two different lines?
Not really. So what you do is, so you take a magnetic core. So you have the cable, the power cable, and then so you have energy produced by the common mode noise. So the common mode energy. So you use a magnetic core, and what you do is that you manage to confine that energy on the ferrite.
So both the power, it's because
Yeah.
any power cord will have two wires at least, isn't
So
it?
you use
You have a main thing
yeah.
and you have the return
Yes. So you put the ferrite over the two cables.
over the both of them.
Yes, because you want to remove the common mode noise.
So that means, so you have some kind of a hollow cylinder and you
Yeah.
let the cable going under it.
That's it.
Oh, I see.
Yeah.
That's wonderful.
Yep.
Okay. And I see. So how does ferrite core do all the magic? Can you just explain?
So as I was saying before, is that we look for, what we want is to confine the energy. So in the end, you want that all the energy, the unwanted energy, stays in your system so that it does not radiate. And the same for the cables. You don't want that noisy signals or...
No, but what is there so special in a ferrite core that it does that and nothing else, and not some other material does it?
So it has a magnetic core, and what it does is that it has a
So
high
it has a high magnetic
permeability, so
Okay.
it manages to concentrate the magnetic fields. And that's why also, depending on the frequency you want to attenuate or you want to remove, you use one core
So how
or
do you
another.
choose the value of the ferrite core?
That's a magic question, eh?
No, but
That's
it automatically came from your last statement.
So how you choose? Normally, what you get from manufacturers is the impedance, and also so an impedance curve, and
It says something like 600 ohms, and possibly it is at some particular frequency.
probably, yeah.
Basically the
So-
frequency multiplied by the inductance.
Yes.
Isn't it?
So there are two approaches. The theoretical one, so you see the impedance, you calculate the impedance and the input, the impedance, the load impedance, and then you do your numbers. The real life, how it works. is-
Actually, you like to know the real life.
You get the catalog of ferrites, you choose a manufacturer, you know that they offer you different ferrites for different frequencies, and you choose the one that has the highest impedance for the frequency you want to attenuate. So imagine you are trying to pass conducted emissions test, you have a problem in 17 mega, so you choose more or less a ferrite that has the highest impedance there. And you try.
So the frequency, so you are basically trying to some frequency band, and let us say this is the center frequency of that band.
Yes.
So it would be that you have to have, the ferrite core should have the highest impedance at that frequency.
Yes, or enough impedance. Yep.
Okay.
That's
So that means all the frequencies below that, ferrite core will have less impedance, so they will pass.
or they will be attenuated, but less attenuated.
But much less.
Much less. Yeah.
Okay.
Yeah,
And the higher one definitely will be attenuated.
Yep.
Okay, wonderful. So that's a very good.
So
Now there is another thing about the power of the current rating of the ferrite core.
okay.
Okay. Now how to choose that?
There you don't have a problem because with ferrite cores, so you use them to filter or to remove the common mode noise. So in the end, so if you have a system that has a rating of 100 amps, so you are going to have 100 amps going in and out.
Right.
So the ferrite is not going to see never 100 amps because the magnetic flux of those 100
Cancel out.
amps is cancelled.
Yeah.
You want to remove 3 milliamps because it's the common mode noise. So that's why the current rating of the ferrite it's not going to limit you.
Okay. So what it means is that it is not the actual magnetic field, whatever is the signal or the power. That magnetic field is not the concern for the ferrite core.
No, it's going to cancel, so no problem. It's not going to saturate because common mode noise.
So basically it introduces a high impedance at that frequency on both the lines.
Yes.
And that is how the common mode is cancelled.
Mm-hmm.
Correct?
Yep.
Okay. Wonderful. So it's a low pass filter kind of thing.
Yes, kind of.
Something of
Yeah. In the end, you are making a filter.
Yeah.
Okay. Impedance.
There is something called a common mode choke. Used to be used in all the power supplies, switching mode power supplies, and other places, etc.
They are still.
In 1970s, I remember I have used a hell of a lot of them.
And in 2025, they are still being used.
They are still being used.
Yes.
So they are useful.
Yes.
Okay. So why are they useful?
So same as ferrites. Let's say that the only difference is a little bit on the moment where people use them. So ferrite bits are or ferrite
on the signals.
Ferrite
bits.
cables are normally used as a troubleshooting element. So when you are in the EMC lab crying and frustrated, and you need to pass the EMC test because your manager is calling you, hey, Ignacio,
put a flight bead on every cable.
Come home with a certificate or don't come at all. So then you start using ferrite cables. And common mode chokes, you use them on the PCB
on the actual
level,
circuit,
so at the design level.
At the design level.
So, but yeah, it's same. You want to remove the common mode noise, and it's also in both directions. You want to filter the noise coming from the outside,
right?
But also
bidirectional.
It's useful.
It does not allow that noise frequencies to pass from this side to that side or from that side to this side.
Yeah, the only difference is that the impedance for one side or the other is going to be different, but that's the idea. So it's useful for both directions.
Sierra Circuits has been working very hard for electrical engineers and PCB designers like yourself on our engineering tools. These are engineering tools to help you design faster. We want to reduce your design time and get the design right the first time. So our top tools on our website, number one is the PCB Stack-Up Planner. Knowing that you have a good stack-up right away for your design. Number two is the bomb checker. It'll do basic scrubbing, make sure your ref deses are good, your NPNs are good, the NPN matches the description. You know, all these are amazing features of the bomb checker. We also have an impedance tool, which is based on Maxwell's equations. And these are all for free for the PCB designer and electrical engineer. You know, please go check them out. It's all for you.
Do capacitors have any role to play?
Always.
How?
So you normally don't use just a common mode choke and that's it. So you combine it with capacitors because you want to build an LC filter.
Okay. So basically L and C.
LCL or combinations of different filters. Okay. Yeah, always. Never alone.
Never alone.
Never alone.
Okay. And the frequency then you choose as per the whatever the frequency you want at the bandwidth for and all that.
Yeah. So for conducted emissions, you measure between 150 kilohertz and 30 mega for the industrial applications. So you need to be sure that in that band,
150 kilohertz for industrial applications.
Between 150 and 30 mega. So you need to be sure that in that range, noise is not very, very high.
Are there any other electronic devices used for EMC? I mean, we talked about capacitors, inductors.
Filtering elements. Filtering elements. Filter elements.
Filter element, or whatever. I mean,
So
they are called EMC filters also many times.
Yes.
These are nothing but those inductance, capacitance filters.
Normally, you build a block.
You build a block.
A block of EMC filters. So they are normally made for big systems, for installations or cabinets.
Right.
But in the end, if you open them, it's a combination of LCL, CL. So it depends on.
I mean, maybe 1 or 2 stages or 3 stages or something.
But for components, so you have LCs, combinations, so common mode chokes, also ferrite bits, so Ls, kind of inductors, and what else? So some variations of those.
So basically, magnetics is the key here.
Magnetics.
I mean, I see the inductance, I can see the common mode choke. I mean, everything seems to be having some relationship to magnetic control, magnetic field control.
Yes. Yeah, that's why I like EMC.
Now I understand how you became an EMC expert. Because your basic field was magnetics.
Yeah.
Okay, wonderful. So is there any shape or something on the printed circuit board other than, having lines, proper separations, proper current capacity and ground planes and all that stuff? Is there anything else on the printed circuit board that one can do?
For
Any particular shape or something like that, or which basically reduces EMC emission on the one hand and EMC susceptibility on the other
Yep.
hand.
So more on the shapes is the stack up. It's more than the
Stack up.
Stack up. So people dedicate very little time to the stack up, and they should spend time to design the stack up. So it's always the
Signals have to be referenced properly
Yeah.
to a ground plane.
yeah, that's it. Yeah. So not a specific shape, but more on okay. You have critical signals. What is the relative positions to reference planes?
We are pretty good at that. I mean, stack up is one of our specialty, especially for a highly controlled impedance, high frequency
Yeah.
stack ups.
Yeah.
And advising on the ground planes and the structures, et cetera, and don't have a split in your ground plane, because otherwise your signal is going to the return path will get.
Yeah, the challenge is that people that are already at that level, that they know that they are controlling impedance, that they use specialized tools to design their stack up.
Right.
They are already they are already skilled. The challenge is the other 70% of people that they have built circuits that work, but never
Pass the test.
Pass the test. Yep.
Are there any difference between American standards and the European standards?
There are a few, so they are not exactly the same, and mainly because here you have the FCC for radiation, so for radio systems. So already frequencies are completely different. So,
I see.
so you cannot transmit at the same bands here and there.
Right.
And also the standard, so the process is not the same. So then it's not enough to certify the product here, in the European Union, and then coming here the next day and start selling. You need to go through different certification processes.
Tell me one thing. Suppose you design a circuit board and it has a wireless LAN on it, which is anyway going to radiate. So will it fail the EMC test or what?
No, so if you add a radio system at your radio device to your system, so you need to do a few extra tests that belong to the radio category, where you check that you transmit only in the band that you are intended.
Okay.
So if it's Wi-Fi, so in the 2.4 giga,
Sure.
really at that band, that you don't invade
The other
adjacent
bands. Okay.
And
So
also-
that test is done.
That's So then is there where you need to combine the EMC part, the classic EMC part, and also the radio
The
part.
radio
Yeah.
discipline part, the band discipline part.
because you can transmit on that band, but you cannot transmit too much. So and also you need to be sure that if somebody generates energy and you take it, your device absorb it, that there are no interferences. So there are also a few tests there. So then but yeah, so you need to go through a parallel process, let's say.
Does any electromagnetic energy that you receive, can it heat up the circuit board?
You mean
Temperature. Can it heat up so much that the temperature rises? I mean,
Maxwell is there, so yes. Still, so to start feeling some heat there, the amount of radiation should be very high. So
intensity has to be.
yeah, the intensity needs to be very, very high. So hopefully you are not even close to that field.
I think mostly we are not.
Yeah.
The only thing is, but since, people sometimes ask, this, there's a lot of
Yeah.
energy and all that stuff, etc.
Yeah, but the level, we're talking about microwatts or micro, so really low energy.
So the amount of the broadcasting electromagnetic energy which you have of so many broadcast HD channels and all that, floating around in the air all the time.
Everything, all we have here, yes.
Yeah. So that does not affect your EMC testing or something like that? Not that much.
Yeah, so that's one of the tests you need to make, is that your system works fine.
Oh, that means the susceptibility part.
Susceptibility
So
part,
it should
yeah.
not be prone
Yeah.
to malfunction as a result of whatever is
Yeah.
spurious electromagnetic energy in the air.
So you have the spurious reception testing
Okay.
and the spurious transmission. So that's really what you test there.
Okay.
Yep. So then.
Wonderful.
Can I switch to the tools,
Yes.
for example? So,
Yeah.
I mean, this was obviously a fantastic conversation. I didn't want to interrupt at all. But from a tools perspective, right, talk to us about your tool and, what benefit does it have for designers?
Okay.
Yeah.
Oh, we have a software tool?
Yeah, we have an online platform. So before, as I was mentioning, that one of the biggest challenges that designers have is that there are a bunch of training resources out there that are useful. That for sure they are moving designers in the good direction most of the times. But the challenge they have is that it's hard to apply those recommendations in their system. So what we are doing is, we're bringing the EMC expertise. So we are covering that gap between all the resources and designers. And what we provide is EMC services. And designers in general or manufacturers are very used to work on EMC at the final stage. Mm-hmm. So the same day they send the files for manufacturing, they say, I'm going to send the files to my friends or to my colleagues so that they can check the EMC behavior. And then it's too late because production is launched. There is no way that they are going to launch a second revision at the time. So then it's very hard to make modifications at the time. So what we are doing is working with designers, manufacturers at the early stage so that they start checking the EMC at the very beginning. So from the requirements phase, schematic, block diagram, really to see what are the gaps. And then we move to the schematic, PCB files, and then we review the...
So
the
schematics also has to incorporate some of the additional safeguards.
Yes, and even requirements.
Requirements.
And block diagram. So grounding is very important. So,
right.
So in the block diagram, then we discuss and we check, okay, how are you going to connect the negative of your board or the reference to the chassis, how many points, what kind of components are you going to use. So we start checking at that point. And how we do it is that, so we have an online platform where we provide personalized EMC assessments. So it has three main parts. So it's recommended detections. So we provide a list of detections, possible areas of improvement, areas where we see that in the end those can provoke EMC problems.
Right.
We explain why those are a problem. So it's not only, hey, you have a problem there. It's, hey, this lack of capacitor or this stack up is going to provoke radiated emissions. So this can be a big issue. And then recommendation, we give a few recommendations, a few alternatives to fix the problems, and also an explanation on why this is beneficial. And then we add an area, or the highlight where this problem is mainly located. And the main reason of giving this structure of detection recommendation is because people are learning while working on their own designs. Because what we have seen is that people are learning with us. So they start with very basic designs. And 6 months later, we have seen that they come with much more advanced designs because they have learned how to implement the recommendations in later designs. So also one important thing is that we don't provide eternal or very long reports. They are short, and this is shocking for people in the industry, because we want people to focus on the most important things. So designers are all stressed because they have a bunch of PCBs to design or projects or many activities. So we don't want to give them 200-line report that they don't know what to look at. What is the most important thing? Should I add a capacitor? Should I change the whole stack up? Should I add a filter? So then what we provide is a ranking. So we give them 8, 10, or even 5. And we tell them, these are the most important things you need to focus. Fix them, and then upload again. So the idea is that they come to us, and then they upload the file they change, and they upload again. Then we check for the next most important thing, and then iteratively in very short cycles, then they reduce the risk of having EMC problems.
So what is it that they need to upload?
So we started with PCB files, mainly working with ODB++ files, but then we learned that people don't certify, don't go to the EMC lab with a PCB. They go with a whole system.
Right.
So then now we are analyzing any kind of file that represents a system. So it can be a schematic files, so the PDF with a schematic file, or an Altium schematic file, or KiCad, whatever tool they are using, PCB files. Also, it can be a block diagram in, PowerPoint, whatever they want to use. Right. So any kind of file that helps us to understand what the system looks like.
Got it.
Well, I think that's a very smart application.
Thank you.
Yeah, I haven't seen this, but I definitely like to get a demo of that.
Whenever you want, you can create an account and start playing with it already.
I'm very bad at creating accounts. In fact, nowadays I'm in the process of closing so many accounts.
No, but I'm sure he'd be happy to, Ignacio would be happy to give us a demo.
No, definitely.
Yes, for sure.
Okay, so I have a couple of true-false questions.
Yes.
Can simulation tools, like yourselves, can they
Is it a simulation tool?
No, we don't want to be a simulation tool.
Oh,
exactly.
That's
sorry. What is your tool?
It's not a
It's
simulation.
not a simulation tool. It's
It's an analysis
It's
tool.
an analysis. Okay. So you're creating your own different analysis.
Yep. Yeah.
Or- okay.
That's it. Also, with the service we provide, it's not only the tool. So with every time that customers upload, they have, so they can book EMC sessions with a team of EMC experts.
Got it.
So it's not only the report. It's not only, okay, report, here it is, ciao, find your way. There is always an
There's
EMC
expertise
expert
behind it.
Yeah, there is a team of EMC
A lot of
experts.
hand-holding is there.
That's great.
Yeah.
This is wonderful.
Yeah.
And then in those sessions we go through the report, but also we discuss any other EMC related topics.
I'm reasonably certain, however much the AI may advance, any AI-based, totally automatic solution for this field is not possible.
We'll see.
So just curious, when did you start your website?
The website,
The analysis on your website?
so the platform, you mean?
Right.
So the company started 2 years ago.
Okay.
So the company was created 2 years, 2021. That's not 2 years ago. 2022, something like that. Yeah.
Okay.
So before we had a different name. It was Mitai, and then 6 months ago we changed the name, and then we are Denpaflux.
Okay. And then, so how many users per month, let's say? Where are you right now?
So
how many designs do you analyze a month?
those are different questions.
Okay. Okay, that is true.
It's
Okay,
true,
the first one.
So-
how many users?
So we are having more because we started with a pilot phase to understand the market, and we're having more and more customers every month. So that's now we're in a good shape. So we're getting I think at 4 or 5 customers more every month. So and it's going up.
It's going up.
Yeah.
Okay.
How much does it time? How many time or number of days, etc., it takes to each project that comes, roughly on the average?
So it depends a lot on the company and also the needs, because that has been one of the learnings. Is so if you see the standard process of EMC, so people have an idea, they prototype, they build a stable device, and then they go to the lab. but it's not true because not everybody wants to go to the lab. Not everybody is ready to sell a solution. They just want to have a double check. So we have seen that not everybody has the same needs, and they come to us with different requests.
No, even if the people are not, let us say, having a necessity to go to the labs, still they will like to see better EMC.
Yeah, so
kind of discipline on their designs.
Yep.
And that is where I think your platform should be of help.
Yeah. So that's what we are seeing is that. So we are working with companies that either they don't have a single euro or dollar to spend on EMC expertise, so because they are not focusing on that, or that they don't have enough projects for that, or with companies that they have EMC capacity or EMC people, but they are fully booked. So then having a meeting with the EMC guy of the company takes 2 months.
I know of a Singapore company who was quite happy selling their product in the rest of the world other than United States. And now they want to set up an export, and suddenly they conducted the FCC check on their product and it failed. So they made an improvement and again it failed. So maybe I'll advise, because they told me and they were asking me, so I gave them some general advice, because they were the stepper motors and high current switching and all that. I said, you better shield your cables. So, but maybe I would direct them to you.
I'm here for them.
RF designs driving you crazy? High-speed PCBs making you question your life choices? Relax, Sierra Circuits is coming to the rescue. We take care of the difficult stuff, and you can take the credit. Visit protoexpress.com and let's make your design the one everybody is reverse engineering.
Perfect. Yeah, actually, I was thinking something similar. So we like customers definitely interacting with us early on, and to get a good stack up.
Yep.
That means we should incorporate some thought process, which I'm sure we do already, for EMC in the stack up. But then when the customer has their preliminary design, let's say, they got their component placement, they got some routing done. Is your analysis appropriate at that time, or is your analysis only appropriate, when the
after the layout is complete?
layout's complete?
No. So we can help at both moments.
Let's say the first step is the schematics. Let us just think like
Yeah.
a schematic has been designed. No layout process has started. Okay. Would it be appropriate to? But we know roughly what the PCB size is and all that.
More or less.
Okay?
Yeah.
So would it be of help at that time?
Yes. So indeed, that's a very good moment to work together, because if the PCB,
That means on the schematics,
but
effectively, what you guys will do is to improve the schematics somewhat, and introduce some components here and there.
Yeah. So one of the things we do is we have EMC, so we have direct contact with the customers, and before starting the analysis, one of the things we ask is what are the restrictions, because for different companies, so they have different restrictions. Some people cannot modify the bill of materials at all, or some other people cannot modify the stack up because they have official stack ups in the company. So I have seen different scenarios. So then with the restrictions we have, then we produce the recommendations, so we work together to improve the EMC. If we have completely freedom, so then we say, okay, this is a stack up, this is what you need to
you recommend the stack up?
Yeah.
Okay.
Yeah. So of course, as soon as possible, that's the best situation, but the industry is not used to look for solutions at the early beginning.
We have
Go ahead.
We have a free stack up tool, a very high quality tool, and all the impedance models are there. Okay, crosstalk.
Yeah.
Crosstalk calculator is
Yeah, yeah.
there. S parameter calculator is
Okay.
there. Okay. So all those things I would suggest or request you to go through that and see if it is useful from your
Definitely.
perspective.
Definitely.
Okay.
Yeah, I have used your tools in the past.
Oh, you have?
Yes, I mean, I needed to design my PCB, so you had a bunch.
Why I was trying to promote it?
Yeah, because you have a ton of useful resources. So I was designing PCBs. I was not manufacturing with you, but the amount of resources you have for designers is amazing. So it's
Thank you very much.
for check the stack up, for check. So as you mentioned, so
Impedance calculator.
impedance, but also the DFM.
Temperature,
The DFM.
current capacity, and all those kinds of things.
The DFM checker you had, I was using it at the time for a complex project. So you have a lot of online resources. So
Okay.
yeah. So no problem. Yeah, but yeah, all those things are very useful because you need to be so as much information you have, so it's going to be useful for you, and changing that when everything is rooted.
See, we have
is a
designed
nightmare.
most of the stack ups with a view to have the best possible signal integrity. And it was, I don't know, I mean, that's what Eric Bogarton says many times, that if you have taken care of signal integrity, you have taken care of the EMC also to a large extent, not completely, but to a large extent already.
You have done already a lot.
So is that true?
Yeah, it's true. That is completely true. Yeah.
Okay, one true or false question.
Yes.
Components with high current draw are less likely to generate EMC issues.
What?
There's a question, true or false?
That's false.
It should be obvious.
Yeah, that was obvious. So reducing trace lengths can help minimize EMI issues.
Yes, it can help. It's not the magic, it's not the silver bullet, but it can help.
Got it. Let's see.
So what are you saying is that reducing the PCB size helps?
Absolutely.
So suppose, then let me put this question slightly in a different aspect.
Please.
That if you start using 2 mil technology instead of 5 mil technology for traces and spaces,
Then you are paying a little bit more.
that's okay.
Assume the PCB is the same cost.
Okay, same cost, flat rate.
But
at TRC
it
rate.
reduces it reduces the size of the PCB.
Yes,
So would that be a better environment for EMC?
yes.
They should be.
If the frequencies are the same, yes.
Yeah, frequency is the same.
Yeah, then yes, because
Wonderful.
yeah.
I think we're going to start marketing our.
If you manage that people use the same frequencies, then go ahead.
Okay. All right. Thank you very much. That's one positive endorsement we have got.
Does using a thicker PCB have any impact on EMC performance?
It's not a weird question. It's one of the most underestimated.
Okay, well there you
Oh,
go.
it's a good question.
Yeah, it is.
This must be his question.
Wonderful, wonderful.
No, it's not mine.
No. Most people don't understand that.
Okay, please explain then.
Explain it.
Yes.
You have a crosstalk calculator, or you don't? You have a crosstalk calculator?
Yeah.
you
Yeah.
say?
Oh, yeah.
So then you know the answer. We'll see.
But
Yeah.
please.
So there is one rule of thumb for crosstalk that everybody knows. That says, so keep distance or keep traces 3 times trace width apart, and that's the rule that everybody has. And then they say, oh, I don't have space, I don't have
Nowadays, actually,
like
in high density PCBs, you don't have that.
yeah, so you cannot do that. But what most of people underestimate is that they can play with the electric. So if you put the traces closer to your ground plane, you
confine the energy.
You are going to confine the energy.
Yeah.
So then you are going to have less.
So which
crosstalk.
means the thinner the PCB, the better it is.
Can be, yeah. So
That means
yeah.
more thick means too much of separation between the ground plane and the.
So
So
that's
that's
why
not
it's-
good.
For the stack up design, you always need to think about coupled
Correct.
pairs. So, and that's why when you have a 4-layer board, that these 2 layers are that far, this trace is not going to be ever the reference plane of this one.
Sure.
So that's why you need to think always between these two. But that means that also in more dense PCBs, you can play with the dielectric to reduce crosstalk.
Good.
So if the center dielectric is really thick,
Yep.
that's
In 4-layer boards, normally, yes. It's like 3 times the
See, the
older
micro
distance.
and that's
straight.
okay.
Yeah, that's okay, but that means that you cannot consider, or you should not consider that the second layer can be the reference plane for the third, or vice versa.
You know, it's perfect.
I
All
I-
our
I-
stack-ups are
I-
definitely have already consulted him.
I approve. I passed the test. Yeah.
Okay. So, let us say the more separation you have between the signal plane and the reference ground plane, the worse is
Yep.
the thing.
Yes.
Correct?
Yes.
So you should go only, so the rule of thumb now I am devising, and please say whether it is yes or not, that consistent with the total number of layers that you have, okay?
Mm-hmm.
And I assume the total number of layers are signal layers and as many plane layers, roughly,
Okay.
okay? Or plane layers are a little bit more than that.
Mm-hmm.
Consistent with that, whatever is the thinnest PCB that you can have,
Yes.
that is always better. Let's say I am designing a 18-layer PCB.
Okay.
Okay.
You are having fun. Yes.
In 18-layer PCB, the minimum thickness I can have is something like 76 mils.
Mm-hmm.
Okay?
Okay.
76 mils. You're familiar with mils. Or
Let's-
should I convert into
No,
microns?
let's
No?
continue. Yeah.
Okay.
Let's see.
So 76 mils, because I realize that you
Yeah,
were
yeah, it's fine, it's
in,
fine.
in
Sure.
Western Europe. So 76 mils is the
The
least
minimum.
thickness.
Okay.
You know, if you take the copper thicknesses of all
Yeah,
the layers and the
plating.
dielectrics, you know, 3 mils and 4 mils, etc.
Yeah, it's already
not more
it's
than
already
that.
tough. It's already tough. Yeah.
So, rather than having a 125 mil board for,
Right.
18 layers, it's better to have a 76 or maybe 80 mil board.
So you need to look for the relative. So in the end, what is most important is the distance between the critical signals and their reference
Oh yeah,
layer.
no,
But
never more than 4.
The total, it doesn't, let's say that it doesn't matter. So the total is going, normally it's given by manufacturing restrictions. So
But
The
we
ru-
are a manufacturer,
The
so we
rule,
know.
the rule of
Yeah.
thumb is that if you are reducing the overall, then you're obviously reducing
Yeah,
the critical references
Yeah,
as well.
that's it.
So it's in the right direction.
yeah.
So
That-
yeah. So rule of
uh,
thumb, it's
It's
Yeah.
okay.
I would give it a thumbs up.
Yeah,
for the rule of thumb.
the challenge is that you change the impedance. So then you need to.
The impedances are the same as
Impe-
desired, 50 ohms, 100 ohms,
Yeah, but
and all
then
that.
that means that you also need to change the traits with. So there
yeah.
is always a trade-off.
You're thinking from you have a design now, you want to shrink it.
Yeah.
So we're thinking from you start off with a thinner.
Okay.
Stack.
Yeah. That's
The reason,
That's it. Yeah.
the
yeah,
reason we raised this question was that many times customer comes and he says, I have a 18-layer board and, my board has to be 90 mil thick.
Mhm.
Why it has to be 90 mil thick? Because, it's 18 layers and all, and, I need some 5-6 mil separation and all. Why do you need that separation? He has no answer. Just because somebody has, tradition or something like that,
Yeah, but
custom.
it's an expensive tradition.
Yeah. So we advise him that that's not very good, neither from signal integrity perspective, nor from EMC perspective.
Yep.
So you better, so consult our table. Total number of layers, what is the maximum copper thickness you have on your signal and plane layers, and this is the minimum thickness
Yeah.
that is possible.
Yeah.
Use that.
Yeah.
We are bringing up that table in our tools. So
That's
we are
great.
creating a tools now for that.
That's a great.
That's great.
That's a great one.
Yeah. That's a good
I
one.
like that one.
Okay.
Okay, another true/false question. Signal integrity and EMC are interconnected.
Yeah. Yeah. US
True.
Yes, true.
Shielding is the only solution to resolve EMI.
False.
False. True, false. Simulation tools can fully replace physical EMC testing.
False.
Poor PCB layout is one of the leading causes of EMC failures.
True.
Higher frequency designs are more prone to EMC challenges than lower frequency designs.
True.
Higher current switching
I
designs
know, that's a better question.
are more prone to EMC.
Higher current switches.
Yeah,
Yes.
higher current switching.
True.
And then, and RF designs. Are RF designs more prone to EMC issues?
Yeah, definitely.
True.
What's the biggest mistake engineers make when designing for EMC compliance?
That they don't consider EMC the
At
design
all.
state. Yeah.
Yes. So what would you recommend an engineer who has very little budget
Mm-hmm.
but wants to be a good engineer and make sure they've considered good EMC practices? What would you recommend they do?
That they consider, that they start allocating some space and resources on the board for EMC, even if they don't have the final answer. But they know, for example, they have the idea that they will need some filters, so to allocate the space, then later for some capacitors, so that they start thinking about it and then figure it out after in later stages of the design. But at least that they have already the mental space and time for working later on EMC.
That was good.
That's good.
That was good.
I was thinking that you're going to say that read this book, Tom Morrison's Electromagnetic Shielding and the EMI.
Yeah, I've done it. Yeah,
That book is good.
I know.
I said little budget, not little time. You're right. What's one simple tip every PCB designer should know to avoid the most critical EMI issues?
If you think that you have spent enough time designing your stack up, spend 10 times more. So dedicate enough time to design your stack up.
Which means a hurriedly designed stack up is a very bad thing.
Yeah.
Or not having any clue about your stack up.
Yeah. Or trusting blindly online stack
So,
reference stack ups.
Lucy, please note, whenever a customer asks for a stack up, we should never give it on the same day.
We do a lot of free stack ups for our customers. A lot.
Okay.
In spite of the fact that we have an online tool.
Yeah, that's true.
Yeah. Okay.
They
Interesting.
become complicated stack ups.
Yeah.
Like a rigid flex with
No, especially
critical
multiple
signals.
laminations,
Mhm.
SDI,
Yeah,
and all that stuff. Okay, good.
And then, so we kind of talked about this a little bit, your tool and your online tool, and then,
Mhm.
and how does it fit into the workflow,
Yep.
right? And right now it's an analysis tool, and you don't want to be a simulation tool. So, because we're in 2025, how is AI going to change your tool?
Yep. So today what we are doing is bridging or closing the gap between designers and EMC expertise.
Yes.
And we are doing it by building the platform or by bringing experts. And today the process, we are totally transparent there. It's very manual. So we have a platform, it works fine, but still it's
A lot of manual.
But we have an online viewer. We have where people can navigate over their boards, and at some point, these tasks cannot be done more automatically, or manually anymore. So then we need to automate. We need to reduce the friction there. So it's clear that there is a future of automation there where we want to automate tasks that are repetitive and that are not adding value because they are the same again and again, and that also that we need technology to help us as CMC experts, but also our customers.
So how soon your AI solution going to come?
Who said AI?
Hmm?
Who said AI?
No, I said how soon?
I said AI. He's saying no AI solution.
who know why? So there,
No, automatic solution.
Automatic.
I didn't say AI.
automated
Automated,
solution.
yeah.
So we have been working on that.
Okay.
So since some time ago, we are developing our own set of tools. Today, tools are more internal, so they are being used by experts
Right.
to make the analysis, but the quality is kind of low. So we need
Throughput is
humans.
also low.
We need humans to filter and
But we would like your platform to be used by every engineer.
that's the goal.
And the target is
Yeah.
100,000 engineers in a year.
That's the thing. And so today anybody can use it, and everybody can upload.
Correct.
But one of the key points is that we want to deliver reports in a very short time, and there is no way that we can do that for
Yeah, you
amount
can't
of
scale.
customers.
You can't scale with
all
the manual experts.
So there is a technology roadmap there to build tools
To help scale.
Yeah.
So
That's good.
So is this technology roadmap being implemented in Munich or
Yes.
United States or in Spain?
We're in Germany, so
Germany.
in Munich,
Okay,
yeah.
Munich. Wonderful, wonderful.
So these are off PCB questions.
Okay,
So not necessarily related to PCBs
Or electronics, yeah.
or electronics, but they always come back to it. But what's your hobby or passion of yours outside of engineering that people may not know about?
Well, so when I am not working on EMC, PCB, or anything related to electrons, so I am into photography or cycling.
Oh, that's great.
Wonderful.
That's where I spend my days.
That's good. That's a good hobby. And if you could have dinner with any DesignCon speaker, who would it be and why? That's very PCB.
That's very PCB. Yeah, I see. So I will say that it will be Eric Bogatin,
Uh-huh.
who is the star and the reference on signal integrity.
Who, Eric Bogart?
Eric Bogatin, and because he has a special ability to make complex things look very easy, and I would love to learn more in
Have you met Rick
real
Hartley?
time. Sorry.
Rick Hartley?
Also, that will be a second option, but I need to choose one.
2 lunches. Second would be Rick Hartley. It's cute.
Naturally, Eric Bogart. Definitely far more flary.
Okay, so and then what's a piece of advice or life lesson you've carried with you throughout your career?
That's a hard one. Because not hard, but yeah.
Basically, like I think that's a good question.
Yeah.
It's like, how do you see yourself in your professional career? Like what's important to you in your professional career?
So yeah, I can say that. So one thing that have helped me a lot. So in my consultancy work and also in my current role where I need to interact with a lot of people, is be easy to work with. So be easy, be reachable, be easy to talk to people, be close to people, and that helped me a lot to connect with people that 5 years ago I will never imagine. So, and I think that it's being very useful for me today.
Oh, wonderful. Thank you.